Good afternoon. This is Jenna Nelson, taking the place of Denise DiMartino and doing the atomic structure and periodicity notes. So the first thing we need to talk about is, since we're talking about atoms and the structure of atoms, we can observe a lot about the structure of atoms by looking at light. According to Max Planck, he did an experiment where he found that the energy of light and the frequency of light are directly proportional, which led us to the equation energy equals Planck's constant times frequency. Energy has the units joules. Frequency has the units 1/second, which you can also see written as per second or as hertz. And then Planck's constant, which is equal to 6.63 times 10 to the negative 34th joules times second. Now, this constant and this formula are all going to be found on that AP equation sheet when you take the test. Now, I've already said that this is directly proportional, but you can see that if you increase frequency here, because you're multiplying it by a constant, it's going to increase the energy on this side. Light can only exist in certain energies, so instead of it always acting like a wave, you can also think of light as acting like a particle. This added to the idea that light has to be quantized, which means instead of it being continuous, you have discrete packages of light called photons. And these photons travel at the speed of light in a vacuum, which is represented by the letter C, and that's equal to the wavelength times the frequency. Speed of light, which is 3.0 times 10 to the 8th meters per second. Frequency, which still has the units 1/second or per second. And wavelength, which has the unit of meter. This equation right here will also be given to you on the AP sheet. Now, if you look at these two equations, you see that they have something in common. They both have frequency involved in them. This one, I guess you can't see which one I'm pointing at. This one here and this one here both have frequency involved. So what you can do is manipulate your first equation, C equals wavelength times frequency, solving for frequency, and plug what you find into this equation over here, resulting in this final equation. I feel like these notes are now a mess because I just colored all over this board. This equation is not on the AP Chem sheet, but I believe you have to memorize it for physics, and it might be nice to know. If you don't know it, simply use both of these equations if you're given energy and you're looking for wavelength, or vice versa. Now, in this equation, we're going to backtrack for a second. Because C is constant, the speed of light is constant, we need to figure out how wavelength and frequency are related. So, if wavelength was to increase on this side, what would happen to frequency in order for it to stay constant? It's going to have to decrease, exactly. So the relationship between wavelength and frequency is indirect or inverse. As one increases, the other decreases. If we look at our combined equation down here, we can also find a relationship between energy and wavelength. As energy increases, what's going to have to happen to wavelength, which is located in the denominator of this equation? It's going to have to decrease, because when you're dividing by a number that's smaller, you're making the entire number bigger. So this is also indirectly proportional. All right, so let's look at a question here. So calculate the frequency of light that has a wavelength of 6.7 times 10 to the negative 5th centimeters. So you're looking for frequency, they give you wavelength. You're probably going to use the speed of light equals frequency times wavelength. The speed of light is always 3.0 times 10 to the 8th meters per second. In this case, the wavelength is 6.7 times 10 to the negative 5th centimeters. Can I plug that directly into this formula? No, I can't, because it's in centimeters and you need the units to be able to cancel. On my notes from demo, it says that you must show that you have done this conversion. So either put it in here and say that there's 100 centimeters in 1 meter. and then multiply it by frequency, obviously solving for frequency. Or you can do this conversion down here somewhere and then show how you plugged it in. But you can't just plug it in and you can't not show that conversion. So when we do the math, we isolate for frequency and we get 4.48 times 10 to the 14th, or to the correct number of sig figs, 4.5 times 10 to the 14th. What are going to be the units on that number? Per second. Your next practice problem says calculate the energy of a photon of orange light with the frequency of 5.0 times 10 to the 14th per seconds. So in this case, you have energy, frequency. You're probably going to use Planck's constant. Energy equals Planck's constant times frequency, Planck's equation. So you're looking for energy here. Planck's constant is always 6.63 times 10 to the negative 34th joules times second. And you're multiplying it by your frequency, which is in the right units, RD and per seconds. 5.0 times 10 to the 14th per second. And when you plug that into your calculator, you get 3.3 times 10 to the negative 19th, and our units are going to be joules. Now this question asks you to find the energy of a photon of orange light. So you're looking for like one of those packages of lights. Your next question here says calculate the energy of a mole of photons of orange light. And the frequency they give you here is 5.0 times 10 to the 14th, which is the same frequency as you had before. So if you know it was one photon was 3.3 times 10 to the negative 19th joules. That's how much energy one photon of light is bringing. What would you have to multiply it for a whole photon of lights? 6.02 times 10 to the 23rd, which is the amount in a mole. So if you had a mole of photons, you'd have 6.02 times 10 to the 23rd. And you plug and chug that into that calculator, and you get 2.0 times 10 to the 5th joules. So if each photon is bringing this much energy and you have a mole of them, that's how much energy you're going to have of orange light. In our next problem, it asks us to calculate the energy of a photon of light with a wavelength of 425 nanometers. In this case, we have energy and wavelengths. You have two options when you're solving these problems. Your first option is to use this formula. Energy equals Planck's constant times frequency. I lied. Your first option is to use this formula. Speed of light equals wavelength times frequency. Plug in the wavelength and solve for the frequency. Then take that frequency and use the other formula to solve for energy. So you can use two separate formulas to do this. Or you can use the combined formula. Energy equals Planck's constant times the speed of light divided by the wavelength. Do you have a preference in which way we solve it right now? The second way? Let's do it the shortcut way. You guys all understand that this formula is not given to you, but these two are. But you can create that formula from these two. Now, on my notes from demo, it says that you must know that 1 times 10 to the negative 9th meters is equal to 1 nanometer. I'm assuming that she's expecting you guys to memorize that. So make sure you put that in your bank of things that you know. So for here, we can start plugging in. E equals, Planck's constant is 6.63 times 10 to the negative 34th joules per second, times the speed of light, which is 3.0 times 10 to the 8th meters per second, all divided by our wavelength. Of course, we can't put it in there in nanometers, so we're going to show our conversion between nanometers and meters. And you can do this conversion out to the side and then plug it in if you need to. So now we can see here that nanometers canceled. We're left with meters on the bottom, which is going to cancel with our meters up on the top. And then our seconds are going to cancel, leaving us just with joules, which is the unit of energy. So we know we've done something right. And when you plug this into your calculator, I end up with 4.68 times 10 to the negative 19 joules. If you had done it this way and you first solve for frequency and then plug that in and solve for energy, you should have gotten the exact same answer. Our next problem says the energy required to break the oxygen-oxygen bond in O2 is 496 kilojoules per mole. Calculate the minimum wavelength of light that can break the oxygen-oxygen bond in one molecule. The very first thing I notice is that they give me energy, and I'm looking for wavelength. So I still have that option to use both the equations for the speed of light and the energy equation, or I can use the combined equation. I'm going to opt to, again, use the combined equation, but either way, you should get the exact same answer. So we're going to use this equation right here. I know the energy, 496 kilojoules per mole, but there's two problems with that number. What's my first problem? Kilojoules. This has to be converted into joules. The other problem with that number is moles. They gave it to us per mole, but we're looking for it in one molecule. So I'm going to take that 496 kilojoules per mole, and I'm going to convert it into joules first. So I'm going to make that conversion line go out. There's 1 kilojoule in 1,000 joules. And then I'm going to convert my moles into molecules, again using Avogadro's number, 6.02 times 10 to the 23 molecules in 1 mole. When I plug all of this in, I find my new energy to be 8.24 times 10 to the negative 19 joules. And this is per molecule, but you don't have to include that because you know your answer is looking for per molecule. This is going to equal Planck's constant, which is 6.63 times 10 to the negative 34 joules times second, all multiplied by the speed of light, 3.0 times 10 to the 8th meters per second, divided by my wavelength, which is what I'm solving for. So when you do those calculations, you find the wavelength to equal 2.41 times 10 to the negative 7th meters. And that's your unit when you go through and you cancel everything out. It's the unit of wavelength. So Einstein stated that energy is equal to mass times the speed of light squared. So we said there's some correlation between waves and particles. So light can be a wave and a particle. De Broglie came around and said that matter, which is made of particles, therefore can also act as both a particle and a wave. It's called the duality of matter, which is correlated to the duality of light. He came up with what's called de Broglie's equation, which makes that correlation between wavelength and mass right here. So again, mass is in the denominator. If my wavelength increases, what's going to have to happen to my mass? It's going to have to decrease, which makes these indirectly proportional, which makes sense, right? A photon of light, which has very, 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 very small mass, can have a relatively large wavelength. Whereas someone like us that has a very, very large mass, it's going to have a very, very short wavelength. A short, short wavelength, so much so that you don't even realize that you currently are walking around with a wavelength. Now, Bohr came around and applied this concept of light to the atom. Zemo maybe wanted to make sure that you guys understand the difference between emission and absorption of energy. When an electron goes from an excited energy state and falls down, it's going to release light. It's going to emit energy in the form of light. You get emission spectra from that. That's this one on the bottom. You can see that depending on how that electron changes energy level, it releases specific bands of light, which are unique for every element. When an atom goes from its ground state and jumps up an energy level, it has to absorb energy in the form of light. And from that, you get your absorption spectrum up here, where now you have all your light present and it's pulling the light out. You'll notice that your bands are in the exact same place, except in this case, you're using the light at those energies, whereas here, you're emitting it. I should say excreting, that sounds gross. You're emitting the light. So there's a difference between emission spectra and absorption spectra. It has to do with whether energy is being released by the electron falling or energy is being absorbed as the electron jumps up into higher energy levels. This leads us to the Rydberg equation. Which says that your energy is equal to the negative times the Rydberg constant times 1 over your energy level squared. Your Rydberg constant, RH, is equal to 2.178 times 10 to the negative 18. So when you plug that in, you get a nice pretty formula that says the energy at energy level N is equal to negative, from right there, 2.178 times 10 to the negative 18th divided by your energy level squared. This is given to you on your AP sheet. You do not have to memorize this. What you do have to know, however, is this equation right here only applies to hydrogen. It can only apply to that one electron. Once you get into atoms that have more electrons, this equation becomes more complicated, so you can no longer use this simple equation to explain it. It's very important that you know that you can only apply this equation with hydrogen. Now, what we're talking about when we use the Rydberg equation is electrons changing energy levels, that one electron in hydrogen changing energy levels. So in order to determine how much energy is either released or absorbed, if the electron is going up in energy level or coming back down in energy level, you just need to take the energy at the final energy level minus the energy at the initial energy level. It's always final minus initial. So if the electron is falling, its final energy level is going to be lower than its initial energy level. So this is going to become a negative number, which makes sense because energy is being released. Whereas if the electron is going the other direction, your final energy level is higher than your initial energy level. So this is going to be a bigger number minus a smaller number, and you're going to have a positive energy, which is the amount of energy it takes to put in. Now, this right here is me simply taking this equation for energy level final and then taking that equation for energy level initial and subtracting the two. You can create this equation using this one equation, and it gets a little different because of the negative signs. You'll see there's no longer a negative here, which pulls the negative out here, which flipped the initial and the final. So now it looks like it's initial minus final. You are welcome to solve this either way. You can do it piece by piece, finding the energy for the final, finding the energy for the initial, and subtracting. Or you can use this one equation. And I'm going to take the next problem, and I'm actually going to solve it both ways for you. So you can see that it comes out to be the exact same. Before I change slides, I told you that this only applies to hydrogen. If you have any other element given to you on a test or quiz or anything like that, you have to be given those energies that you find the difference of. You cannot calculate it using this equation. So our problem says, calculate the energy emitted when an electron falls from the 4th energy level to the 2nd energy level. And then from there, it asks the second question that says, what is the wavelength of light emitted? We're going to do that at the very end. First thing I want to do is look at the energy. The Rydberg equation says that the energy is equal to negative 2.178 times 10 to the negative 18th divided by the energy level squared. And I told you it's always final minus initial. What is the final energy level that I'm at? 2. So my final energy level in this case is 2. My initial energy level is 4. So what I'm going to do is I'm going to calculate the energy at energy level 2, and then I'm going to subtract it from the energy at energy level 4. So I'm going to use this equation right here, negative 2.178 times 10 to the negative 18 divided by my energy level, which is 2, squared. And I'm going to subtract it from energy level 4. So negative 2.178 times 10 to the negative 18 divided by my energy level 4 squared. So your change in energy when you fall from energy level 4 to 2 is negative 4.08 times 10 to the negative 19 joules. Negative because you're falling, you're emitting that energy. Now I'm going to take a second and I'm going to use that other equation that we gave you for change in energy, and I'm going to show you how you could use this equation and solve for the exact same answer. So this one is 2.178 times 10 to the negative 18th, but it's positive, and it's times 1 over your initial energy level, which is 4 squared, minus 1 divided by your final energy level, which is 2 squared. And if you plug this into your calculator, you find your change in energy to be negative 4.08 times 10 to the negative 19 joules. So we found the energy in both cases, which is what the first part of this problem asks us to do. The second part asks us to find the wavelength of that light emitted. So we're going back to our original equation. I'm going to use the combined one where energy equals Planck's constant times the speed of light divided by the wavelength. Our energy was negative 4.08 times 10 to the negative 19 joules. But I don't really need this negative here because we're talking about light being emitted. We're talking about energy in its holistic sense. So the negative is telling us a direction that the energy is going, so we don't really need it. You're not going to end up with a negative wavelength. Doesn't make any sense. Times 6.63 times 10 to the negative 34th joules per second times the speed of light, 3.0 times 10 to the 8th meters per second, all divided by that wavelength. So you can isolate the wavelength and solve for that. Here we go. So when you plug and chug that into your calculator, you get 4.88 times 10 to the negative 7 meters. And chances are, if you had a problem like this, they wouldn't want it in meters. They would ask for the wavelength in nanometers, which would end up being 488 nanometers. And you could make that conversion pretty simple. I love this next question. When Demo showed it to me, it got me all excited, like an electron in its higher energy state. Will a photon of light that has a wavelength of 480 nanometers excite an electron in the hydrogen atom? So we know we can use that Rydberg equation. From the first energy level to the second energy level, explain. So when you think about this, what they're saying is, I'm going to give you this wavelength, which has a specific amount of energy involved. Is that enough energy to make the electron jump? So we need to figure out how much energy we have and how much energy we need. So first we're going to calculate how much energy we have. We're going to use energy equals Planck's constant times the speed of light over the wavelength. 6.63 times 10 to the negative 34 joules times second times 3.0 times 10 to the 8th meters per second, all divided by our wavelength, which is 480 nanometers. So we need to make sure we convert that. 480 nanometers 1 nanometer is 1 times 10 to the negative 9th meters. And when we plug that into our calculator, we get, which is, I said that already. Do you have the answer? That's a double cliffhanger right there for you. That's 4.14 times 10 to the negative 19 joules. So this is the amount of energy that we have. This is the energy they're telling us we have. Now we're going to calculate how much we need to actually make this jump happen. So here's the Rydberg equation, your energy, and do you guys want me to do the two separate ones and subtract, or use the combined one? The combined one sounds great. So the change in energy is equal to positive 2.178 times 10 to the negative 18th, all multiplied by 1 over your initial energy level. So what energy level are we at initially? 1 squared minus your final energy level, which is 2 squared. And when you plug this into your calculator, you find the answer to be 1.63 times 10 to the negative 18th joules. Now, this is how much you have. This is how much energy you need. Do you have enough energy to make that electron jump? Is this number bigger than that number? No. So the answer is nope. The electron will not jump to the higher energy level if you put a photon with a wavelength of 480 nanometers into the atom.